Hey guys, in this lesson we would understand what is the formula that is going to be used for calculations involving equilibrium. For doing calculations in equilibrium, we need to understand equilibrium constant first. Equilibrium constant is represented with K with uppercase and subscript EQ. Now this KEQ has a formula. Let's see how to get that formula. Let's take up an example equation and we take N2O4 gaseous gives us 2NO2 gaseous. If the system is under equilibrium, that means the rate of forward reaction and the rate of reverse reaction is equal. That we have already discussed in the previous lesson. And always remember, this equilibrium constant can only be used if the system is under equilibrium, or if the rate of forward and the rate of reverse reactions are equal. Now we know from the chemical kinetics units that rate is written as rate constant, that is lowercase k, it's not uppercase k. Equilibrium constant is uppercase k, rate constant is lowercase k, and then we have concentration of the reactants. So here goes the concentration of reactants raised to the power of the order of those reactants. Therefore, we can say rate equation is equal to rate constant times the concentration of reactants of that reaction raised to the power of its order. This order is determined experimentally. Now we would use this formula to put in here. So rate forward. For forward reaction, we have N2O4 giving us 2NO2. The rate equation will be lowercase k. We would represent it as k forward because we are writing the rate for forward reaction. In the bracket, the reactants for forward reaction is N2O4. So we would take the concentration of N2O4 raised to the power of the order of N2O4, and we consider that these reactions are single step reactions, so order will be same as the balancing moles. These balancing moles are also called stoichiometric coefficients, so we would write it down as raised to the power of 1. Similarly, the rate law or rate equation for the reverse reaction is when 2NO2 is going to give us N2O4. So we would write down K reverse, concentration of NO2 raised to the power of stoichiometric coefficient of 2. Now here we have to remember that K equilibrium or equilibrium constant is always equal to K forward divided by K reverse. This K is the lowercase k, or the rate constant forward divided by rate constant reverse will give us equilibrium constant. Therefore, we can use this formula and let's find out what is K forward divided by K reverse equal to. K forward, we would take this on the other side and this is being multiplied, so this will get divided here. K reverse would be equal to, this would be moved on the other side. We have NO2 concentration square over N2O4 concentration to the power 1, and this would be nothing but equal to K equilibrium, because K equilibrium is K forward over K reverse, and that is equal to this. So finally we can write down K equilibrium is equal to NO2 concentration raised to the power of 2 divided by N2O4 concentration raised to the power of 1. And when we notice this here in the reaction, because our technical reaction was this way forward, we would just say that K equilibrium is concentration of products raised to the power of its stoichiometric coefficient divided by concentration of reactants raised to the power of its stoichiometric coefficient. These powers, these are basically balancing moles. The other name of balancing moles is stoichiometric coefficient. So that's why we write it down as stoichiometric coefficient. So finally, K equilibrium formula is concentration of products to the power of stoichiometric coefficient divided by concentration of reactants to the power of stoichiometric coefficients. Here we have to remember one important thing is that this concentration is not at any time. This concentration is equilibrium concentration because K is determined at equilibrium. Let's find out K equilibrium for this reaction. We have lowercase a plus lowercase b gives us lowercase c plus lowercase d. These numbers, these lowercase variables would represent the stoichiometric coefficients, and these will represent the reactants. These will represent the products. So we know A, B, C and lowercase d is stoichiometric coefficients. We know K equilibrium is rate constant forward divided by rate constant backward. Or now we also know K equilibrium is concentration of the products divided by the concentration of the reactants. So we can take it like this. We have two products in this case. So we would take individual concentration of the products. So concentration of product C raised to the power of stoichiometric coefficient of C times concentration of D raised to the power of stoichiometric coefficient of D divided by concentration of A raised to the power of stoichiometric coefficient of A times concentration of B raised to the power of stoichiometric coefficient of B. And this is how we write down K equilibrium formula. Now one more thing here to note is that if K equilibrium is equal to 1, we know this is going to be equal to 1 when the numerator and the denominator will be equal. Or we can say the equilibrium concentration of the products and the reactants are equal. That means this is the state of equilibrium. So equilibrium is achieved. If K equilibrium value is greater than 1, that means equilibrium lies to the right side. Or we can say that the system has passed equilibrium. If K equilibrium value is less than 1, that means equilibrium lies to the left side. If equilibrium lies to the left, that means other words we can say forward reaction is favored. If equilibrium value is greater than 1, equilibrium lies to the left. If K equilibrium value is greater than 1, then equilibrium lies to the right. That means reverse reaction is favored. So if we have K equilibrium value here equal to 3, let's say, we know K equilibrium is greater than 1. Therefore, equilibrium lies on the right side. So equilibrium lies to the right or equilibrium lies on the right side means if we consider equilibrium in the form of a number line, and let's say here K equilibrium is equal to 1, anything beyond 1 means products are greater than reactants. If equilibrium is below 1 or if it lies on the left side, that means reactants are greater than products. And equilibrium equal to 1 means products and reactants are equal. And why is this scenario? Because we know K equilibrium is the ratio of product concentration over reactant concentration. So if products and reactants are equal, K equilibrium ratio will be 1. If products are greater than the reactants, then the numerator is greater than denominator. So K equilibrium will be greater than 1. If products are less than reactants, or if reactants are greater than products, that means your denominator is greater than the numerator. So K equilibrium value will be smaller than 1. This is what we need to remember in terms of K equilibrium values and their relationship between the product and the reactant concentration.